Yes, it's working now. Can you send that link to the to that SGTSGI group, WhatsApp group? Okay. Otherwise, you can send it to me. I can also forward. We are missing all our committee members. So, Professor Santanu Misra, Professor Santanu Bose. Hope they will join soon. Hello, sir. Dilip, sir. How are you, sir? It looks like the cold has subsided finally.
Yes, but I'm right now in Kolkata.
Oh, you are in Kolkata. Then there is, yeah, it's warm, I guess.
It is not. It's not too bad in Roorkee also.
Okay.
Calcutta is a surprising March, February end, still not uncomfortable.
Oh, that's good to know.
Yeah.
So give it another 5 minutes, then we will
Okay.
start,
All right,
Abinash,
no problem.
Yes, sir.
so that everyone joins. Okay, before we start, let me just tell you something that I hope all of you have received the first circular of the RDS 8 multiple times. Can someone confirm? Is there anyone who has not received?
I think we all have received, and we will again remind everyone
Yes.
in the beginning of the next month.
Yes, we will do that.
Tomorrow, tomorrow or day after tomorrow in the weekends, we'll circulate again.
So I will encourage that. Please submit your abstracts.
Sorry.
Please submit your abstracts as well as circulate amongst your network and encourage as many people as possible to submit abstracts as well. The registration link is also open, so if you want to register well in advance, that is also possible. Everything is done. Okay, I think then let's just start today's meeting. Thank you everyone for joining this afternoon. And I hope there will be more people joining as well soon. So today we have a very young researcher, Abinash Bal. He is a Ph.D. student from IIT Kanpur, the Experimental Rock Deformation Laboratory, and working with Professor Shantanu Misra. And I think he has done his master's from IIT Bombay. And he is going to speak about from sorption to slippage, experimental investigation on the complex stress-driven flows in anisotropic and fractured shale reservoir. So with this small introduction, may I invite Abinash to deliver his talk, please. Abinash.
Thank you so much, sir.
Put the presentation in the presentation mode and start talking. Okay, thanks.
Thank you, sir. So, is it visible?
It's all good. Go ahead.
Yes, sir. Good afternoon, everyone. I am Abinash Bal. I am a doctoral student in Experimental Rock Deformation Laboratory. I'm working here for last 5 years in the IIT Kanpur. So my overall PhD topic is nano to mesoscale investigation of shale gas recovery. So basically it is completely a experimental based work where we try to understand the storage, transport and recovery in the shale. So if I explain myself, I do explain myself as experimentalist, broadly working in the field of rock mechanics and rock physics. So today I am going to present a part of my PhD work to understand the complex stress-driven flow behavior in the anisotropic and fractured Indian cells. So before I start, I welcome you all, and also at the same time I express my gratitude to SGT-AGI core members and specifically Professor Jyotirmoy Malik sir for allowing me to present my PhD work in the SGT-AGI platform. So before we start any work or doing any research on a particular topic, there are two fundamental questions arises. Why you are doing this, and second question is how your research going to solve this. So if I answer my first question, why I am doing this, so according to United States Energy Information Administration 2011 report, there are about 290 trillion cubic feet shale gas present in India, and out of which 63 trillion cubic feet can be recoverable. But unfortunately, till date, there is no single successful shale gas producing well present in India. So if I go to second question, how my research going to solve this? So there are three fundamental factors that controls the shale gas extraction, that is storage, transport or recovery or enhanced recovery. So to regulate all these fundamental factors, there are few petrophysical properties that control all these parameters, like the shale is abundant of nanopores, which control the storage potential, and it is also important to estimate the pore accessibility. That means how much percentage of pores are that are connected and how much percentage of pores are that are not connected. And next, what is the fluid flow behavior? The shale is a compressible matrix. It creates a complex fluid flow behavior, and which is really creating challenges for the planning of exploration. And finally, the propose a more suitable specifically for the Indian shale gas reservoir. What is the best enhanced fracking techniques that is suitable for Indian shale gas reservoir? So before I start, let's go to the what is conventional, what is unconventional reservoir. There are many definitions to define what is conventional, what is unconventional. But if I and according to Aguilera 2016, he provided the simplest form of definition, that any rock containing hydrocarbons that has permeability greater than 0.1 milliliter C is conventional. Any rock, and any rock that containing hydrocarbon has less than 0.1 milliliter C is unconventional reservoir system. So now question arises, why we are moving towards unconventional reservoir system. So basically, in each year, the demand of natural gas is increasing in an alarming state. That means 20% increase per year, which burdening the Indian economy $120 billion annually. So the Ministry of Petroleum Science and Ministry of Petroleum and Natural Gas is keen to explore the unconventional reservoir system. Unconventional reservoir system means that is tight gas, coal bed methane, shale gas, and gas hydrates. So, but each of these techniques are the cost of production, cost of each of the techniques is quite sophisticated as well as not cost effective, because there are many inherent challenges associated with the production of unconventional reservoir system. Here today I am focusing on the what are the challenges associated with the shale gas recovery. First and foremost, the shale has extremely low permeability and porosity. Second is the nanopore dominant matrix. That means the pores are in the scale of nanopores. And third is high matrix compressibility and anisotropy. Pore heterogeneity and accessibility. And as you know, in the shale, not only there is one single gas, there are maybe multiple gas or fluids present in the shale. Their interaction with the matrix is very difficult to decouple. So to understand all these properties, actually I have tried to cover in my PhD. And first two parts, that nanopore characterization, pore accessibility, we have already published. Now I am focusing on the fluid flow behavior in the shale gas reservoir, which is in under review in energy and fuel. So why it is so complex? If I define that hydrocarbon in the shale mostly present in three form. One is adsorbed form, that is attached to the surface of the matrix. One is dissolved form, that means the hydrocarbon is dissolved to the kerosene or the organic matter, and there are few amount in free form. And the flow behavior also again divided into two types. One is surface diffusion, that means along the surface the gas diffuses, and one is bulk diffusion. And again the bulk diffusion is divided into three types, that is slippage, whether there is slippage, transition, or free molecular path. So the flow regime is very complex inside the pore matrix, nanopore matrix of the cell. So in this study, we try to know how gas flow between these complex pores, and what is the role of how the permeability, anisotropy, and sensitivity of the cell, and what is the effect of serving non-serving gas on the permeability, and finally to develop a fluid flow model. So for that, we have collected deep down core samples from three important petroliferous basins of India. One is Cambay Basin, one is Bengal Basin, and KG Basin. These are the core samples having diameter of 10 centimeter and length varies from 20 to 30 centimeters. And then we code out 1 inch cores from each samples in different direction, bedding perpendicular, parallel, as well as along the fractures, to experimentally study and understand the flow behavior in cell matrices. So before that, we have to know what they are composed of. So for that, we have done X-ray diffraction study for the mineralogy, and rock eval pyrolysis for the kerosene study. And in the XRD study, we found that the KG basin, these two samples, actually we have done in series of total 18 samples, but I am only showing the four samples. So broadly, if I say the KG basins and Cambe basins, the primary clay mineral is the kaolinite. Whereas in the Bengal basin, the primary clay mineral is light, chlorite, and muscovite. So, and if you plot in the ternary lithophases, we found that the KG basins that is represented in the blue colors are mostly mixed and clay rich, whereas the Cambasel are mostly clay rich sediments. And if you plot from the rock eval pyrolysis, if you plot the S2 versus TOC, we found that all the samples we have collected from the KG, Cambe, and Bengal basins have very good to excellent, means the red color is for Cambe and blue color for KG basin. So you can see very good to excellent TOC content. And S2 generally represent the recover potential. What is the hydrocarbon generation potential? So we found that it is mostly good to very good in both Cambe and KG basin, but it is poor in Bengal basin. So to find out why it is poor, then we have plotted in the modified Venn Cleveland plot, and we found that the Bengal basin is thermally immature, but the KG basin and Cambe basins are thermally mature, and they mostly type 2, 3 are mixed type. That means they can produce both oil and gas. So to study experimentally the flow behavior in a cell matrix, we used 1-inch core flux, 1-inch diameter of core flux, and used a pulse decay permeameter instrument. This is an in-house facility in experimental rock deformation laboratory, and this is a unsteady state permeameter in which we put the sample here. This is the sample chamber. We put the sample here, we apply the desired confining pressure. Suppose let's say we collect the samples from 2 kilometer depth, corresponding confining pressure we apply here. Then using different different gases, suppose let's say we want to measure the apparent permeability using nitrogen gas, then we inject certain amount of pore pressure in both upstream reservoir. That means V1 and V2 is the upstream reservoir, V3 and V4 is the downstream reservoir. So let's say we apply a 100 psi or 105 psi. I'm just giving hypothetical value. Then we apply both 105 psi and 105 psi in the both upstream and downstream, and we wait for the equilibrium in the both upstream and downstream. After equilibrium, we close this BV2, that is this valve and this valve. Then we bleed some pressure from the downstream reservoir. That means we bleed some pressure from V3 and V4. That will create a differential pressure in the upstream and downstream, and then we allow the gas to flow through the sample, and the time it taken to equilibrate, that means this is, suppose let's say we started the upstream reservoir pressure is here, this is the downstream pressure. So with time, what happened when the gas flow from the upstream to downstream, this pressure decreases and the downstream pressure increases. So the amount of time it is take to get equilibrated, from that we estimated the apparent permeability of the sample at that condition, means at that confining pressure and at that pore pressure. Here the confining pressure is simulating the overburden pressure and pore pressure is simulating the reservoir pressure. And by using this formula, this is actually not the actual formula, but this is the most simplified equation to estimate the apparent permeability. But before that, before measuring the apparent permeability, that is two things very important. One is pre-stressing, and that we call a seasoning of the sample. Why it is important? Because shale is a compressible matrix. So if you do loading and unloading, suppose let's say when we start estimating the apparent permeability, we apply a loading cycle and unloading cycle. We found that at same stress condition, while loading and unloading, that is forming a hysteresis curve. So that means you have to to eradicate this, we do second cycle. We do second cycle of loading and unloading, and we found that after 2 cycles, the apparent permeability at each stress condition mostly overlapping. So after that only, so that therefore whenever you are using any compressible or any rock type, pre-stressing is very important to accommodate the stress. Then you can, so that you can exactly simulate the reservoir condition. Then you start your experimental condition. Then you start your applying test condition and measuring the apparent permeability. In our case, what happened, we kept the confining pressure constant. The pink color is for confining pressure, and we decrease the pore pressure stepwise. That means we kept the pore pressure here, we measure a permeability, then decrease it, then again measure a. Why we have done this? Because generally what happened, a reservoir is generally located at a particular depth. So that particular depth is corresponding to a particular overburden pressure, and that overburden pressure is correct. And at that overburden pressure, we continuously excavate oil and gas. What happened, the pressure of the reservoir is decreases. So to simulate that, we have done in the experiment, we have followed these test conditions. And we found that this is actually showing one sample of bedding perpendicular sample using nitrogen gas, and we found some interesting results. So if you see here, when depletion means when we excavate oil and gas, that means when you decrease the mean pore pressure, what happened, the apparent permeability is decreasing, which is quite normal. But after certain pore pressure, we are finding that the pore pressure is increasing. In what happened, in conventional reservoir system, it is generally decreases, but in unconventional reservoir system like shale, we found that at different confining pressure, the curve is nearly showing same trend. That means initially it decreases, then after certain pore pressure, after certain it increases. So whether it is consistent with the other unconventional rock, so we have tried it in coal samples, also in the tide sandstone. Actually, we found the similar trend. So why this is happening? This is happening because there are two governing factors that controls the apparent permeability in a cell. Suppose this is a diagram which of a constant confining pressure. Here, this is the apparent permeability curve. So when the depletion initially started, actually it is mostly controlled by the poroelastic effect. That means it is mostly function of effective stress. So that means when reservoir pressure decreases, effective stress increases, which decreases the apparent permeability. But after certain pore pressure, what happened? The apparent permeability increases because here the another governing body, that is fluid dynamic effect, which mostly controlled by the mean free path of the gas and the effective diameter of the conduits through which the gas passes. So when the mean free path is equivalent to the effective diameter of the channel, actually the gas tends to slip along the planes, and that actually increase the apparent permeability. So whenever we are modeling or trying to propose a reservoir plan in the reservoir scale, we have to know exactly where the poroelastic effect and fluid dynamic effect decouple, and that pressure, so that we can accurately estimate the exploration potential of the reservoir. And along with that, there is one more thing is very important, that is effective stress law. That is in simple language, the effective stress is the difference between the confining pressure and the pore pressure. But in nature, actually, pore pressure is not always it is not exactly multiplication of one factor. Its value may increase, it can be greater than one, it can be less than one. So depending upon the matrix type, actually its value changes. So it is very important to estimate the value of effective stress coefficient. Actually, it generally termed differently in soil mechanics. They generally call it Biot's coefficients, which is defined as the ball compressibility of the matrix at constant pressure, constant confining pressure, to the compressibility of the matrix at constant pore pressure. So if you see and it actually provides sensitivity of the reservoir pressure and sensitivity of pore pressure, so that the final effective stress can be determined very accurately. So when it is greater than 1, when it is less than 1, generally, suppose let's say a matrix having high competent clasts, and in the intergranular space, let's the high compressible clay mineral is deposited. So here the sensitivity of pore pressure is relative, the compressibility of the pore pressure is relatively high compared to the outside compression, that means the overburden pressure. So that in that case, the sensitivity of pore pressure is greater than 1. But in sample like shale, coal, where the matrix are mostly composed of clay and different organic matter, which are highly compressible. That means the effect, the compression, the compression by the overburden pressure, compressibility by the overburden pressure is relatively high, and relative to the compressibility of the pore pressures. In that case, the value of less than 1. So how we have estimated the, so therefore it is important to estimate the value of effective stress coefficient. To estimate that, what happened if you plot the apparent triaxial diagram between the apparent permeability, mean pore pressure and confining pressure, actually it will create a 3D surface, and if you project that surface to the plane, basal plane of mean pore pressure and confining pressure, it will give you the isopermeable lines. So these are the isopermeable lines of equal permeability. Actually, this line helps you to decouple exactly where the fluid dynamic effect is governing and poroelastic effect is governing. And we found that in most KG cell, it is a sample of KG cell, it is decoupled around 6 MPa pore pressure. So before that, as you can see, the apparent permeability increases, but after fluid dynamic effect, we found that the slopes of the lines are mostly similar. So actually, if you draw a tangent to the slopes of this line, actually that provides you the value of chi, and we found that in our kg samples the value of chi is 0.64. So far, if I conclude, what are the things we found? We found that the isopermeable lines are initially decreases, then increases, and it is governed by two factors. One is fluid dynamic effect, that is also called slippage effect, and at higher pore pressure there is poroelastic effect that governs the apparent permeability in cell. And also where the fluid dynamic effect and poroelastic effect decouple at 6 to 7 MPa pore pressure, and we also estimated the value of effective stress coefficient, that is around 0.64, which is less than 1. Then we are interested to study the depleted cell gas reservoir. That means we are interested in the fluid dynamic region. Why it is important to study flow in the depleted reservoir condition? It is because when the reservoir pressure decreases, the uh, hydrocarbon generation potential also decreases. Along with, when the reservoir pressure decreases, what happens? The effective stress increases. When the effective stress is so much that if it is overcome the strength of the rock, that means that will induce new fractures, or that also can reactivate the existing fractures. So in the severe case, that may also the entire basin can subside. So it is important to always to maintain the reservoir pressure, so that it will increase the exploration potential, as well as we can eradicate this, we can get rid of this hazards. So for that, for now, there are different gases, means gases that are flooded into the reservoirs to maintain the hydrocarbon, to maintain the reservoir pressure. So which is the most suitable gas? That is a question. So to answer that, actually we have performed apparent permeability in some sorbing and non-sorbing gas. Sorbing gas means those gas which adsorb to the surface. Non-sorbing gas, actually they don't interact with the matrix wall. So we have used 4 gases. Here we have used 2 non-sorbing gas, helium and argon, and 2 sorbing gas, nitrogen and CO2. And this is completely of the depleted reservoir condition, and we found that different gases have different apparent permeability. So why this is happened? And we found that helium has the highest apparent permeability at same stress condition. Suppose let's say this is the diamond symbol is depicting the 5 MPa confining pressure, and these are the yellow color for helium, blue color for argon, pink color for nitrogen, and green color for CO2. And we found that helium at same stress condition, the helium has the highest apparent permeability, followed by argon, next nitrogen, next CO2. That means helium, both the non-sorbing gas have apparent permeability, higher apparent permeability, whereas the sorbing gases have the lower apparent permeability. So why it is happening? We found that the adsorption affinity of the gases is quite, the absorption affinity play crucial roles in the apparent permeability. So CO2 has the higher adsorption affinity compared to all of the gases, so they tend to interact the wall, they adsorb to the surface, and therefore the apparent permeability is decreasing. And as I have previously said, if you in the depleted reservoir condition, what happened? The If you increase the mean pore pressure, this is decreases. So you can found same trend in every gases. But and if you see, if you plot the Terzaghi effective stress with the apparent permeability, it is increasing. In general, what happen if you increase the effective stress, generally the permeability should decrease, but here it is increasing because it is in the depleted reservoir condition, and in the depleted reservoir condition, as I have said, the fluid dynamic effect or the slippage effect is dominant, so that increases the apparent permeability. We have done similar test in the bedding parallel as well as fractured samples, and we have, but the important key thing is that intrinsic permeability is the intrinsic property. Okay, that means this is the liquid permeability which have no slippage when we assume that there is zero slip boundary. So if you estimate the liquid permeability, therefore we try to estimate the liquid permeability by using Klinkenborg correction. It is generally applied for the gases, and also we can estimate the slippage factor. To estimate the intrinsic permeability, if you plot the apparent permeability with respect to inverse of mean pore pressure, apparent permeability inverse of pore pressure at different confining pressure, and if you fit a line, if that is fitted by a straight line, the slope will provide you the intrinsic from the intercept, sorry, the intercept will provide you the intrinsic permeability, and from the slope we can estimate the slippage factor. After correction, you can see that the intrinsic permeability is intrinsic permeability is decreasing with the confining pressure, or we can say it also decreasing with the Terzaghi effective stress. So this is the summary of the all three samples, that is bedding perpendicular sample, bedding parallel samples. Means bedding perpendicular means when the flow is bedding perpendicular, and when the flow is bedding parallel, and this is a fractured, we fractured the sample along the bedding parallel, and we joint it and we estimate the permeability, and we found that in each cases the intrinsic permeability is decreasing with the confining pressure, and here also we found that the helium has the highest intrinsic permeability, followed by the argon, then nitrogens, then CO2. But there is, and we found that the intrinsic permeability in the bedding parallel sample in the lower pore pressure is relatively high compared to the, here it is nearly 18 microdarcy. But here if you see, this is the blue color is for CO2, here the blue color, here the maximum is for 4 microdarcy. But we found that after increase of when the confining pressure is greater than 12 MPa, its value decreases very rapidly. So here we found each sample, after we tested in 2-3 samples, we found that after 12 MPa the intrinsic permeability is less than the bedding perpendicular sample. So why it is happening? If you answer that, suppose let's say this is the thin section of the bedding perpendicular sample and this is the bedding parallel samples. When you flow through the bedding perpendicular sample, here the flow is mostly, the flow conduits of flow channels are mostly matrix dominated. That means the intergranular matrix channels are mostly controlling this flow behavior. But in the bedding parallel samples, there actually, that is inherent bedding parallel microfractures. That is the dominant conduits which controls the flow in the bedding parallel samples. And we found that these bedding parallel microfractures are highly stress sensitive. Therefore, after 12 MPa, we found that the intrinsic permeability of the sample for same gas is less than the intrinsic permeability of bedding perpendicular samples. And there is also important factor, slippage factor. two important observation we found that bedding perpendicular samples are mostly showing mostly linearly varying with the confining pressure, but in the bedding parallel and fractured samples, specifically for the CO2 gas, it is not following a linear path. It is following a non-linear exponential curve. So we found that not only the anisotropy controls the stress sensitivity, but also the type of gas also controlling the sensitivity of the flow. And again, we try to estimate, okay, suppose we have used 4 different gases uh, for our estimation, and we try to know, okay, what is the maximum pores, what is the minimum size of pores that it can be penetrated. So here the average pore width, and from the slip, actually it is calculated from the slippage factor, and we found that the circular symbols are for the CO2 gas. All the circular symbols is for CO2 gas, and is applicable for all type of samples. So this is CO2 samples, and the diamond is symbols is for nitrogen gas. And we found that CO2 can penetrate the smaller pores. That means it can penetrate the smaller pores of the in the scale of, when I'm saying smaller, means that is in the scale of nanometers, that it can penetrate up to 3 nanometers, whereas the other gases it cannot penetrate that much. So that is also providing a crucial findings that, okay, CO2 can penetrate smaller pores relative to the other gases. We also establish a fluid flow model for the depleted reservoir conditions. And if you see, these are the boundary conditions for the different gases. The blue color is for helium gases, the orange is color for argon gases, yellow for nitrogen gases, and the purple is for CO2 gases. And these are the different average diameter of the different samples, so that we have created the flow regime for different flow regimes. So if you know the pore pressure and the average diameter, you can estimate by using the Knudsen number, you can estimate the what is the which type of flow mostly controlling the flow in a cell matrices. And we found that if we plotted our samples, that is KGC3, this is a bedding perpendicular sample is shown in the pink color, and this is a fractured sample is shown in the light green color. We found that different gases have different flow behavior, but mostly the bedding perpendicular samples are mostly flow in the sleep flow regime or transition flow, whereas the fractured sample, we found that it is bouncing initially it was flowing in the Darcy flow. That means it is mostly governing by the Darcy flow, but very depleted reservoir condition, the sleep flow is governing this. So what is the implication of this study? The most implication is that as we know, shale is a impermeable rocks, so we generally frac the samples using mostly currently in the hydraulic, that means using water, and so that we can increase the permeability. But we are saying that instead of using water, if you use the CO2, because why supercritical CO2, why you are saying that? Because it has a higher adsorption affinity, low apparent permeability, and higher penetration capacity. So if you frac with this CO2, supercritical CO2, in that case what happens, it will enhance the permeability, as well as it has higher adsorption affinity. The gas that has been adsorbed on the surface of the wall, that can be dissolved. That means that CO2 can be adsorbed in the surface, and the hydrocarbon that is attached to the surface can be dissolved. So the permeability, the exploration potential can increase. And as we have used different type of anisotropic samples, like bedding perpendicular, parallel, and fractured samples, so that these results, when someone is extrapolating this result, when extrapolating to the reservoir scales, our results will be very helpful to model in the reservoir scale. So in the conclusion, we found that, okay, not only the gases, but not only the anisotropy, but also gases is very important to control the permeability. As we can see, the helium has the highest permeability, but carbon dioxide has the lowest permeability. For both storage for carbon storage as well as enhanced oil gas recovery. So it is currently I'm working on this, and that we have actually installed a high pressure temperature triaxial fracking setup in our experimental rock deformation laboratory, which has a capacity of 2500 kilonewton load frame, 200 MPa confining pressure, 150 MPa top and bottom pressure, and having temperature maximum range of 200 degree. So here currently I am trying to understand the thermohydromechanical behavior of Indian cells, and also we also trying to do the hydraulic fracking, see whether why it is not feasible in an Indian scenario. So in the first two parts, I have said the nanopore characterization, the accessibility. We have already published. If anyone feel interesting, can go through it. Thank you.
Thank you very much, Avinash. Very nice talk and very detailed as well. Before we open up the question answer session, I just have one small point of discussion that you have collected 3 cores from 3 basins. And then you are claiming that you are characterizing the Indian shells.
No, sir.
How justified is that?
We have collected many cores. We have collected many cores from the from same basins.
No, 3 wells, right?
Yeah, 3 wells.
So that means only 3 headline information.
Yeah, that is also, you can say this is the limitation, but the currently the problem is that ONGC is not keen on drilling more.
No,
Or
my just one small criticism that I have, that claiming it for a study on Indian shell is slightly I should say optimistic, because that this is hairline information. I mean, think about hundreds of squared of kilometers of each basin, and then one single point which is 3.5 inch, right? So think about it, whether you should reframe your statement that you are characterizing the Indian shell. Maybe concentrating on one basin with multiple wells could have been, I don't know.
Actually, they have
approach.
Actually we have approached the ONGC. Actually, it is a collaborative project with ONGC. So they haven't actually collected multiple wells. So yeah, you are correct that okay. When I am actually, that's why I have said all this observation in the experimental, in the lab scale, and therefore most of my observations are not limited to the Indian basins. So we are trying to finding some general governing principle that controls the permeability, that means stage dependent permeability. So in the first part, we are saying that okay, these are the 2 governing principle that controls the apparent permeability. But what's true, to claiming to a reservoir scale, Indian cell reservoirs, we need more samples and we need more rigorous estimations to claim our results.
Yeah, I mean, I'm reiterating, sorry for that. Only one core data from one basin doesn't even, talk about something which is away 1 kilometer away from that well, right? So unless you have certain, distribution of wells, more number of well data, it becomes really, challenging to call it an inventory for, or some final words on the Indian shell. So that's my only feedback. I now open it up for question and answer. Yeah. Sir, you might have a question. Dilip sir.
Okay. Up to small, there's a very good talk, no doubt about it. Very detailed work. And I'm glad to note that people are moving away from depending only on deep and strike. Different kinds of applied structural geology problems are being taken up. Having said that, I have 2 points. One is right at the beginning you said shales have very low permeability and porosity. They have very low permeability, but they don't have very low porosity.
Sir,
So
actually we have
if my understanding is correct. And secondly, you used gases such as argon, nitrogen, and so on. Why you didn't use C1 to C4 gases such as methane, ethane, and so on?
actually the problem we also thought about you have to use the methane ethane, but for that we have to have a proper as these are mostly combustible gases, right? So for that we have to have a proper lab and we have to take permission from the institute, because in each iteration of the estimation you have to release some gas, so that gas must be released in a safe way so that these are flammable gas. So if anything, that's why we haven't considered that, but we have thought about that to use the methane ethane and other gases. And
Okay.
if I answer the first question, sir, we have estimated the porosity using helium pycnometer. We also done the nanopore characterization, and mostly in the Indian cell, we found that the maximum porosity, the porosity ranging between 3% to 6%. So which is quite relatively less compared to other samples.
That's kind of surprising.
Yeah.
That's kind of very surprising because shale has higher porosity than usually, normally. Shale has higher porosity than sandstone, for example.
So cell actually the mud, if you say the mud has the clay has the higher porosity, but when it is compacted, the cell mostly the porosity ranging between the maximum, we can say the back end cell has maximum porosity of 11%, not more than that.
Okay, any other question from the students especially? Shantanuda, you have a question.
No, I didn't say that. But of
I
course,
saw that you are about to speak.
no, no. The thing is, I want to congratulate Avinash.
Thank you, sir.
It's a very nice talk. I liked it. So the thing is, you are working with a very sophisticated instrument, and you are trying to talk about things which can, if we can implement that, we can have more recovery from non-recovery wells, right?
Yes,
That you
yes,
said.
yes,
So
sir.
just I wanted to know, you said that effective pore pressure never remain uniform all through. So what are the factors that control the pore pressure?
Sir, pore pressure, when actually pore pressure mostly controlled by the reserve. That means what is the pressure present in the reservoir scale. So if you continuously excavate some oil and gas continuously, the pore pressure means that the reservoir pressure will decrease.
Oh, but in that pore, do you think that in that pore everything is, there is nothing is there?
No, there might
Otherwise,
be.
otherwise, if I think that all the ports are vacant and you have extracted everything, that area should collapse, right?
If the effective strength is greater than the strength of the rock, then that area will collapse. That also depending of the strength of the rock.
Yeah, but the rock that you are dealing with, the strength is very low.
Yeah, but the porosity also very low. That means suppose let's say in a conventional reservoir system where the porosity can vary from 20 to 30%, and if you continuously excavate oil and gas, the time will come when the effective stress will increase so much that it will surpass the strength of the rock. That might create two problems. First, that can deactivate the already faults, because reservoir is a very large reservoir, can scale up to kilometers and kilometers. So in that case, that might reactivate the fault. Also, that can also generate new faults or joints. So if you don't control that, if you don't maintain the reservoir pressure, in some scenario you can find that the entire subsidence of the
So how do you maintain the reservoir pressure?
by flooding some gas that I have said. So generally, what happened in the depleted reservoir conditions, they generally flood some gases like nitrogen, carbon dioxide. We inject through a well to the gas to maintain the reservoir pressure.
In that case, the fluid pressure should be uniform, right? If you inject some gases
Yes.
into the system, then fluid pressure would remain same, I think.
No, sir. Sir, that depends at what rate you are injecting. If the rate of injection and also what is the time that is taking to equilibrate it in the entire reservoir. So if you continuously pump some gas with time, what happened? The reservoir pressure will be maintained.
Avinash, Shantanu, can I come in here? Actually, what
Yes, sure, sure.
happens, you have in a oil and gas reservoir, after your oil or gas leg, you have a water leg, right? And
Yeah.
if your permeability is sufficient enough, essentially whatever oil or gas you take out, that is being replaced by the water. And hence the reservoir pressure is maintained.
Yes.
However, the process of injecting further gas or water falls under enhanced oil or gas recovery. There you try to, if the permeability is not sufficient enough or the water sweep is not happening very efficiently or fast enough, then you try to maintain the pressure introducing some injected water or gas, right? However, in many cases, if the permeability is sufficient enough, the reservoir pressure is maintained by the sweep, the replacement of the port volume by water, which
Yes, sir.
is just beneath the gas leg.
Yes, sir. Sir, currently, actually, there are many reservoirs in the US. Actually, they are injecting carbon dioxide because they found that the depleted reservoir are the most suitable and practical solution for long-term storage of the carbon dioxide. So they actually injecting in mega scales so that they can increase they can store the gas for the longer period of time at the same time also maintain the reservoir pressure.
Okay. So several times you have used the term fluid dynamic effect.
Yes, sir.
What does that mean actually?
Actually, generally, what happened when the permeability is simple definition of permeability, how easily a fluid flow through the sample. So that is
Yeah.
controlled by the fluid channels. So what happened when the fluid channel is very large and the diameter of the fluid channel is very large, that mostly in that case the flow behavior is controlled by the effective stress. That means if you increase the effective stress, the pore conduits will decrease and the permeability will decrease. But in gas, particularly in the gas permeability, what happened? A effective stress come where the mean free path, just I am showing here. Actually, this is the suppose this is the effective diameter. This is the mean free path. Mean free path is the maximum distance covered by a molecule before it further collision or deviating from its path. So this is the mean free path. When the mean free path is equivalent to the effective diameter of the conduits, in that case, what happened? The gas mostly collides. Just a minute. What happened? In that case, the gas mostly slip through the plane, and that will increase the permeability. So that's why we generally it when the mean free path is equivalent to the effective diameters, that mostly then we call that, okay, this is the fluid dynamic effect or the slippage effect which controlling the uh, fluid flow behavior. But it is constant to the gas, and it is constant when the diameter of the conduits is equivalent to mean free path of the gas.
So how do you control the mean free path?
So this is a characteristic property of the gas itself. We don't control. So let me.
So the behavior will change from well to well.
No, so this is the mean free path equation. So this is completely depends upon what temperature. This is a Boltzmann constant, and this is the diameter of the gas. So this is a intrinsic property of a gas that varies according to the temperature and the pore pressure.
Okay. So if pore pressure increases,
If
what will
if the
happen?
pore pressure increases, that means in that case the lambda will decrease.
Yeah.
What happen if the pore pressure will increase? If the pore pressure will increase, what happen? The pore conduits dilates. So in that case, the lambda is minimum.
Okay. Okay. Anyway, I need to look at your work more rigorously,
Thank you, sir.
and only I will be able to understand completely. All the best, Avinash, for your good work, and I hope your work will also give us much understanding about the carbon dioxide sequestration also, or not.
Yeah. Yes, sir.
You are putting your work on that line, I guess,
Yes, sir.
so
Yes, sir.
that you can also insert carbon dioxide to generate hydraulic fracture. So not fracturing, not hydrofracture, but fracturing, right?
Yes, sir. Supercritical CO2 fracking.
Okay. Thank you, Avinash.
Thank you, sir.
Okay, any more question? Anyone?
Yeah.
Yeah, Asutosh, please go ahead.
Yeah, thank you, sir. Hi, Avinash. Thank
Hello,
you for
sir.
the beautiful presentation. Congratulations for all your hard work. Can you please go to slide number 18?
Yeah.
Yeah, I just wanted to learn one thing that, when we consider ECBM with the help of CO2, what usually happens is initially we have a very good acceptance rate of the gas into the coal seam, but with time, what happens? This acceptance rate decreases, or in other words, you could say the permeability drops because of the matrix swelling.
Yes,
So,
sir.
can we expect this kind of a process when we flood CO2 into the shale gas reservoir? Can we expect this kind of a swelling?
The swelling effect is not so prominent in the cells. Actually, I have seen few papers. Yes, there is slight swelling effect, but this is not so much prominent in the cell.
Sorry, could you please repeat? Your internet probably is, the connection is a bit weak. I couldn't
Yes,
hear.
actually, the swelling effect is there, but it is not that prominent in the cell matrices as compared to the coal. Coal mostly we see the due to the adsorption of CO2, the swelling effect is quite dominant, but in cell matrices it is not so dominant. So uh, actually
So
we
we
haven't
can,
checked it. We haven't checked it, but there are few published paper. They have seen that okay, this is not that dominant comparable to the coal samples.
so it is, you mean to say it is safe to ignore?
Yeah.
Okay, okay, thank you.
May I add something, Abinash, to
Yes.
the question of Ashutosh? So, in case of ECBM, the thing that happens is the flow, the swelling is due to the adsorption of gases. So, the time scales are different. Adsorptions happens at a much slower rate, but the flow happens due to the pressure gradient between the atmospheric pressure and the pressure beneath the well. So the adsorption induced swelling that you were talking about is a very later phenomena if we are continuously depleting CBM recovery. It's not for the initial stages because the time scale of the processes are different. Am I clear? Because swelling takes a much longer time because the adsorption processes are slower and flow is a much faster process in terms of time scale.
Yes. Yes. Thank you.
So this would probably correct you. So Abhinash, I just had a simple inquiry. So can you
Yeah.
go to slide 16?
16.
Have have you means this seems that there's a lot of difference between the slippage value between the carbon dioxide and nitrogen. So have you checked in other papers from USA that for a particular confining pressure that this is the amount of difference in slippage for CO2, because the physically it should be controlled by the diameter of the molecule. So CO2 is smaller than nitrogen, but other than that, means it seems that the values are far apart. Means what could be the possible reasons?
Actually, I have checked few papers. They are giving few explanation that yes, the diameter of the CO2 is smaller, but it has higher adsorption affinity. So they tend to collide with the walls more frequently compared to the nitrogen gas.
So if they tend to collide
They
more frequently,
means they
so
tends to slip more readily.
yeah, so the blue symbols are for what? Are for CO2, right?
Yeah, this is the blue. This is for CO2.
Hmm.
This is also for CO2, but this is for the kgJ1 sample, and this is for the B24P. Matlab, this is for
Okay. I misunderstood the
so
diagram.
the
Sorry
both
for
the
that.
samples for CO2 and these are samples for nitrogen.
Okay. Sorry. Then it's perfectly fine. Sorry, I thought it was of CO2 and the green is for nitrogen. So that's why, because these are so small, the fonts I could not
Yes.
recognize between. Okay, great. So that's it from my side.
Thank you.
Okay.
Jyotirmoy,
Yeah.
can I ask another thing, but just to
Yes.
learn?
Yes. Go ahead.
Abinash, what is your
Yes.
opinion regarding this Bengal basin? Why the recovery is not there? What is controlling factor? Your clay mineral?
Yeah, no, sir. The currently we found that Bengal basin is thermally immature. Yes, sir. Yes, it has higher organic content, but
Yeah.
currently it is thermally immature. So actually, we cannot produce oil and gas in the current scenario.
Okay.
There is no storage potential. Actually, it is thermally immature.
Thermally immature. Okay. So at what depth you generally need to go for thermally mature?
Actually,
Oil?
actually it is mostly controlled by the pressure, temperature, and
Uh,
it also depends on the time scale. So so currently in the current scenario, what we have collected, it is thermally mature, but I don't know exactly how much time it will take to come into the mature window. But
okay. At what depth it is there?
the Bengal samples are mostly from 3 kilometer depth.
Acha. Okay. And for kg samples, you are getting at a higher depth? Or?
Yeah, kg samples, yeah, it is in between 29302. That also nearly 3
3
kilometer
kilometers.
depth. And but in the Cambasel, it is ranging from 1403 because there are two formations, younger Cambasel and older Cambasel. So it is ranging between 1500 meter to 2500 meter.
Okay. Okay. Thank you.
Thank you, sir.
Any more queries from anybody? I think Professor Dashgupta is smiling. You may ask something.
You're referring to me, Professor Bose?
Yes.
Oh, no, actually, Avinash, I missed a great part of your lecture because I had a practical class. I'm sorry for that. I'll surely revisit it in the YouTube. I'll have time in the field.
Yes, sir. Thank you.
So I'll do that. Must have been a very good lecture, as I gather from the comments of the earlier speaker people. And it was nice looking at Manav also, who happened to be my student long back, seeing his face after a long time. While following the discussions, but I must admit that I have not heard your considerable part of your lecture. But following the discussions, I was thinking when Shantanu prompted, uh, is there a role of mineralogy in this process? It has
Yes,
variable
yes,
contents of different clay minerals as well as quartz.
yes, yes. Actually, that is a great role in the actually persisting. Suppose we frac a sample, what happened? That is the most in we found that in the kg cell, the clay content is very high, which is 60 to 70%. That increases the plasticity. So if you frac the samples, the fractures are not persistent for a longer period of time. That is actually a main challenge. We've generally they found in enhanced fracking techniques in the cell gas reservoir of kg cells. And so if you have inorganic minerals like quartz and feldspar, actually that promotes more brittleness, so which favors the fracture of the samples.
And also the different types of clay minerals, as Manu was telling, that the timing of the processes, even the absorption process also varies in time scales between the different clay minerals.
Right, right.
So it's a very
Actually,
complex situation, and I have not gone through your presentation, but you must have discussed the nature of the variability of these clay minerals both along the length and across the basins. Have you shown any such thing in your earlier slides?
no, actually we have only
Some
collected the
sort of
samples.
petrography to differentiate between the porosity things that Dilipda was also talking about. I mean, that everything is controlled a great deal by mineralogy. I mean,
Actually, we found that in the KG, mostly KG and Cambe basin, the primary clay mineral is the kaolinite. So
okay.
if I show you the diagram, so we found that in the KG, basin, these are the two KG basins, and this is Cambe basin. The dominant clay mineral is the kaolinite. But in the Bengal basin, we found that the dominant clay mineral illite and chloride. Yes, it is true. Different minerals have different structure, as you say, TOT tetrahedral, octahedral, tetrahedral structures. So they have also different, uh, as Manavda said, they have different adsorption affinity for different gases. They also have different swelling property. That also controls the amount of porosity or the amount of gases. But we found that here, as the samples are mostly kaolinite, and the porosity is not varying that much. It varying in between 3 to 6%.
You don't have carbonates, any sizable proportion of carbonates in these places?
Siderite, we have siderite as a carbonate.
Where, oh, I cannot read it. Okay, fine.
Green
Siderite.
color, green
Right,
color.
right. Yes, that is a very important mineral. I mean, these carbonates play a great role.
Yes, sir.
Okay, thank you. I mean, I must admit that my fault, my sorryfulness for not attending your lecture from the beginning. I'll definitely see it once. Congratulations.
Avinash, never-ending process. So in your title you have put sorption, right?
Yes, sir.
But you talked more about adsorption, not absorption.
Sir, actually, sorption is a process that actually defined both adsorption and desorption.
No, absorption and adsorption.
Adsorption, ADSOR.
Yes, adsorption and absorption both simultaneously, right? So far I understand. Sorption means simultaneously you are having adsorption on the surface as well as in the absorption
Yes, sir.
inside.
Yes, sir.
But you talked more about you concentrated more about the surface thing.
Yeah, but in the cell, actually, there are as I have said, cell, the hydrocarbon mostly present in three form, both adsorbed form, dissolved form. That is, you are saying adsorbed form, and as also free form. Yes, but the contribution of the dissolved form is very less, which is less than 10%, and mostly in the cell, the dominant is the adsorbed form and free form.
Okay. Okay. Okay, we must give a big round of applause to Avinash, I think.
Thank you, sir.
I don't know if anybody has to ask anything, any query, any clarification. I think it's done.
If there are no further questions, then let us just close this for today. We will send you invite for the next session as well for next month. And please, again, I'm requesting, please submit your abstract, register, and circulate the invitation to your network. Thank you very much.
Thank you.
Chalo,
Thank you.
bye-bye.
Thank you, everyone, for your attention and feedbacks. Thank you.
Take care, Abinash. Bye.
Thank you, sir.
Bye-bye, everyone.